Okay, so let's start today's session. The first speaker of this session is Marianna Russkikh. So she's going to talk about Lozenge tilings on a cylinder. So please.
Thank you for the introduction. And hello, everyone. Thanks for coming. This talk is based on joint paper with Andrew An and Roger von Peski. And I'm going to tell you about, so we're interested in Lozenge tilings on a cylinder or equivalently cylindric partitions. So to be certain that we're all on the same page, let me first remind you a basic definition on partition and plane partition before jumping into cylindric partitions. So ordinary partitions are non-increasing arrays of non-zero integers with finitely many non-zero coordinates, and there are many ways of depicting them, and the most common and used one is a Young diagram or Ferrar's shape. So here is an example of a partition together with its Young diagram, and it is known that ordinary partitions are in bijection with Young diagrams. Okay, so a plane partition is a way of filling boxes of the square grid in a quarter plane with non-zero integers in such a way that when we move to the infinity in the directions of the grid, then the numbers do not increase, and we also ask that the total number of non-zero entries is finite. Note that a plane partition can be seen as a collection of finite number of unit cubes stacked in a convex manner in the corner of an infinite room. And here the entries of plane partition are simply the corresponding stack of cubes. Also, one can think about a plane partition as a tiling of a triangle lattice by lozenges of 3 types with the following boundary conditions. So in each 2 pi over 3 quadrant, all but finitely many lozenges are of the corresponding type. Or in other words, we're interested in lozenge tilings which differ from an empty room configuration by a finite number of lozenges. One may also consider a room with a jagged wall that has several corners, which correspond to plane partitions of the same set, but with the same some squares removed from the corner. And finally, a cylindric partition is a way of filling the boxes of the square grid, which is wrapped around a cylinder. So this is a cutted version of some picture like this. Yet again, with non-zero integers in such a way that when we move away from the border of a half cylinder, then the numbers do not increase, and also we ask that the total number of non-integer entries is finite. Note that in this case, one can also think about cylindric partition as a stack of cubes in a corresponding empty room. So if you want to think about a real cylinder instead of a cut one, so you can think about a stack of cubes around infinite top hat. Now the question whether we also have these nice interpretations with Lozenge tilings of the infinite cylinder with some boundary conditions. So what are the boundary conditions in this case? We are that all lozenges, if we go far away down, are horizontal when we go to minus infinity, and when we go to plus infinity, the lozenges just alternate between these two types. So the picture far away up looks like this. And this is our boundary conditions. So another way, we can also say that those are configurations which differ from empty room configuration by a finite number of lozenges. And so the question is whether cylindric partitions are in bijection with tilings with these boundary conditions. And the answer is no. And before I explain you why in this cylindric partition case we don't have this bijection, however, in a plane partition, everyone knows that this bijection works. Let me tell you what we mean by a random tiling or random partition in the plane partition case. So as we know, in a plane partition, tilings and partitions are in bijection. So I can think about random tilings instead of random partitions. And one of very natural ways is you can say that all configurations are equally weighted to deal with so the probability of such configurations is 1 over the total number of tilings. And another natural measure with respect to the this stack of boxes interpretation is Q to the volume measure, where we say that the probability of corresponding the probability of a given tiling is proportional to Q to the volume of this tiling, where the volume is just the number of cubes in terms of this unit cube interpretation. So in this case, for this picture, the volume is, so what do we have here is 1, 2, 2, 2, 3, and 5. So the volume is 5 plus 3 plus 3 times 2 plus 5 plus times 1, which is 19. So the probability of this configuration is Q to the 19. And note that this Q to the volume measure give us a probability measure even if we look at infinite number of all set of plane partitions. Okay, so now what is the problem with Lozenge tiling interpretation for the cylinder? Let's consider these two Lozenge tilings of a cylinder, which differ by a shift. So we just consider this tiling and shift it by 1 in which direction? Yeah, and we just shift it by 1. So note that these two configurations cannot be obtained one from another by adding or removing unit cubes. However, each Lozenge tiling configuration with our boundary conditions correspond to some empty room. So this is always true that one can remove all boxes and get some empty room configuration. But there are different empty room configurations which differ by a shift. And note that one empty room cannot be obtained from another empty room by adding or removing unique cubes. So it seems that it is natural to look at the pairs of cylindric partitions together with a vertical shift, integer vertical shift. So we should do the following. So we should fix an empty room configuration. Let's say this one. And then other empty room configurations which are obtained from this one are shifted empty room configurations. And now the set of Lozenge tilings with fixed boundary conditions and infinity are in bijection with the pairs of cylindric partitions together with the integer shift. So which gives rise to think about two different setups for the cylindric partitions. The first one is to think about Q to the volume measure, which is supported on cylindric partitions with probability of cylindric partition proportional to Q to the volume. And the second setup is think about these pairs of cylindric partition and some vertical shift, or equivalently the set of Lozenge tilings of the cylinder with our boundary conditions. And the probability of, so let us consider Q to the volume distributed cylindric partition together with some integer valued random variable. We will discuss later which distribution is natural to choose for this random shift, for this vertical shift. But what we want to know now is that these two things are independent. So we think about pairs of independent cylindric partition and vertical shift. And they are distributed somehow, where we discuss later the probability of the distribution of this integer valued variable. So we have two natural steps. One is Q to the volume measure, and another one is so-called shift mix Q to the volume measure. I will give precise definitions a bit later. Right now, I hope that it's clear that there are two different steps, where one is dealing with cylindric partitions and another one with the pairs of a cylindric partition and the vertical shift, which is equivalent to think about Lozenge tilings with boundary conditions fixed at plus and minus infinity, as we described before. Okay. And now one of the most important objects in the Lozenge tilings is the height function, and this is what we're interested in. So given a Lozenge tiling, one can define a height function on vertices of a tiling, which is defined as follows. So we just write in each vertex the height of corresponding stack of boxes. Or another way to define it is that, okay, given a Lozenge tiling, we fix a height function to be 0 at some point. So we say that the height function here is 0. And then at all other vertices, the height function is defined by these local relations. Note that the height function uniquely defined the phi function is defined up to by this local relation is defined up to additive constant. Then we fix it at some point. So there is a bijection between height functions which satisfy these local relations and Lozenge configurations. And then if we want to think about Lozenge configurations with some fixed boundary conditions, then okay, we should also fix some boundary conditions for the height function. So instead of a Lozenge configuration, one can think about random Lozenge configuration, one can think about a random height function. Therefore, key questions in the Lozenge tiling model concern the large-scale behavior of the height function and of its fluctuations. So we are interested in the limit shape of the height function and the scaling limit of the fluctuations of the height function. And here are results. So for both cases, Q to the volume measure and shift mix Q to the volume measure, we found a limit shape, which is actually was already computed in the paper by Alexei Borodin, and our only real input is showing some concentration. And other results which are really new and wasn't studied before are fluctuations of the height function for cylindric partitions. And here are main results. So we show that the fluctuations of the height function in the Q to the volume distributed cylindric partitions, so where we think about partitions only without a shift, so unshifted Q to the volume case, they converge to the Gaussian free field in some precise conformal structure, which is called the Kenyon-Okounkov conformal structure. And in the case of shift mix Q to the volume distributed cylindric tilings, when we have a shift as well, the fluctuations converge to the Gaussian free field with the discrete Gaussian shift. So the fluctuations again here converge to the Gaussian free field in Kenyon-Okounkov conformal structure. But here, in addition, there is a discrete Gaussian shift. And the goal for the rest of the talk is to clarify the statement of those theorems, to give precisely the definition of the model, to explain what is GFF and Kenyon-Okounkov complex structure. Are there any questions so far? Okay. If not, then let me start with a toy model, which is nice to have in mind. And one can think about these as a one-dimensional version of the height function. So let us consider a simple random walk started at 0 and conditioned to end at x. Or equivalently, one can think about the uniform measure on the set of these up-down path from 0, 0 to xt. And it is known that if x and t goes to infinity in such a way that the slope remains constant, then the limit shape is simply a straight line between those 2 points. So, in other words, the random walk is concentrated around this line shown in blue. So this is a limit shape result for a simple random walk, and it is also well known that in this setup, the fluctuations convergence to a standard Borodin bridge. In particular, the covariance computed at 2 points S and S prime converge to a covariance of a standard Borodin bridge, which is given by the Green's function for the Laplace operator on 0-1 interval with zero Dirichlet boundary conditions. So here is a example to have in mind. And now let me say a few words about Gaussian free field, and recall that we expect the fluctuations of the height function converge to the Gaussian free field in some conformal structure. So what is the Gaussian free field? If you never heard about it before, you can just have in mind this picture, which is actually a simulation of discrete Gaussian free field approximating a continuous one, and think about it as a two-dimensional analog of the Borodin bridge, which we just discussed. More precisely, the Gaussian free field is a Gaussian process with a covariance kernel given by the Green's function of the Laplace operator. Note that the two-dimensional Gaussian free field is the random generalized function or a random distribution, so it's not a random function. So the value at that point is not really defined. And in terms of test functions, if you smooth the Gaussian free field against the test function, then the covariance functional may be seen as a standard Dirichlet energy of the domain. So this is an analog how to think about covariance in the case of Gaussian free field, but not a Borodin bridge. So it looks similar, but one should think about test functions. Okay, and as I said, the fluctuations of the height function converge to the GFF in some conformal structure. So what do we mean by this? And let us consider a simple example where it is known. Let us think about uniform Lozenge tilings. And here is the picture of how a generic uniform Lozenge tiling look like as a mesh goes to zero at a large scale. And this is well known, and you can see that there is a different behavior close to corners and inside the circle, so-called Arctic circle. So the liquid region, which is a region where the asymptotics of probabilities of lozenges of all three types are non-zero. The fluctuations of the height function inside the liquid region, in the case of the uniform Lozenge tilings of the hexagon, is known to converge to the Gaussian free field, but in a new conformal structure. So one should map this liquid region to a unit disk with a sum map, which is a precise map. And what is important about this map is that this map is not conformal. So we change the conformal structure. We get a GFF in a liquid region in some new complex coordinates. By the way, this is a theorem proved by Leo. Here is a conjecture made by Kenyon-Okounkov. And the statement of the conjecture is the following. So for Lozenge tilings, actually more generally for Dimer model on biperiodic bipartite planar graphs, there exists a map on a liquid region, so that such that the fluctuations of the height function converges to the Gaussian free field in this new conformal structure. So this map introduces a different conformal structure on a liquid region, which is different from one it inherits from the plane in which it naturally lives. And this conformal structure is actually defined in terms of the limit shape of the height function. And here is a theorem by Kenyon-Okounkov that for the in the liquid region, yet again, recall that the liquid region is where the probabilities of all three types of lozenges are positive. There exists some function which is related in the following way to the limit shape of the height function and satisfies some differential equation. And this map zeta, which defined a new conformal structure, is given in terms of this function z. In the case of the uniform measure, it is just coincide with z, and in the case of q to the volume measure, okay, it is given in some way, yet again, in terms of this function z. Okay, so now let us discuss some known results about limit shape and the fluctuations. So first of all, about the limit shape, Kenyon and Prop showed that the normalized height function converged to a certain entropy maximizers for uniformly random dominant tilings. And then Kenyon-Okounkov and Sheffield generalized this result for weighted doubly periodic bipartite Dimer models, not only for the uniform random dominant tilings on the on this Dimer model on the square lattice. Then Okounkov and Russkikh showed the limit shape result for the q to the volume ordinary plane partitions, and the convergence of the fluctuations to the Gaussian free field in this case was shown by Andrew An. And then also there are some results for the convergence of the fluctuations to the Gaussian free field for certain domains on the square lattice and hexagonal lattice, as well as, okay, this is also some results for the Dimer model on the hexagonal lattice. And on the Holey's table of results, there is this result which I want to emphasize, since it is a result for a non-simply connected domain. All other results shown here are done for simply connected domains. And we will go to this hexagon with a hole later on. So today we're going to discuss q to the volume distributed cylindric partitions and shift mix q to the volume distributed cylindric partitions. Okay. And now let me finally define the model, which was introduced by Alexei Borodin and also studied by Dan and Jeremy. Okay, so we have two setups, Q to the volume measure and shift mix Q to the volume measure. Q to the volume measure is supported on cylindric partitions. And here we want to consider a probability measure on this full set of Lozenge tilings with those sort of boundary conditions at the infinity. And Q to the volume measure, which we had just here, is only a measure on the restricted set of cylindric partitions, or in other case, when the shift is fixed to be 0. So a very natural notion of the measure on the full set was introduced by Alexei, called the shift mixed Q to the volume measure. And one way you can view this is you have a Q to the volume distributed cylindric partition, and you also have a integer valued random variable, which is distributed in a following, in something like this. So the probability of S is equal what is here, what is written here. And we think about a pair of independent cylindric partition and integer valued random variable. Okay, there are few reasons why it is natural to think about, first of all, to think about a pair of the cylindric partition together with a shift, and why it is natural to choose a shift distributed as it's shown here. So Alexei also introduced in this work a periodic Schur process, which is more general than what we have here. So this is a measure supported on cylindric partitions, where the probability of which a cylindric partition is given in terms of Schur's Q functions, and Q to the volume measure is just a particular case of this periodic Schur process. And he also introduced this shift mixed periodic Schur process, and okay, like one of the motivations was that this periodic Schur process allows to study random cylindric partitions in the same way as original Schur process introduced by Okounkov and Russkikh allows to study the random plane partitions. And this periodic Schur, this point process, like the point process, which is naturally associated to this cylindric partition, requires non-trivial shift mixing to be determinantal. So if we think about shift mix periodic Schur process, then it happened to be to have a determinantal structure, and this is why this is very natural choice of deal with the partition together with the shift, because here the periodic Schur process itself is not determinantal. And another reason why the shift is natural, we discussed it already, if we want to think about Lozenge tilings of the cylinder with fixed boundary conditions, but for the in this setup, one can also define a weighted dimer model, which gives the same measure as the shift mix periodic Schur process. So as I mentioned, Dan and Jeremy also studied this model, and so they gave an alternative
We seem to have lost the speaker.
I don't know. Maybe she's stalled now. So we have to wait. Oh.
Marianna, we can't actually hear you or see you.
Okay, something happened to my laptop. I don't know what, it's just died.
Yeah.
Okay.
Now it's okay?
So, no, I mean, I don't know what's wrong with my laptop, but I can use just my tablet, so you can see and hear me, which is good, right?
Yeah. So you can go on, I think. So, okay.
So you
yeah, for the moment
still see my screen, right?
Yes. Now yeah, we see your slides. Yeah.
You see my slides. Okay, great.
Yes, yeah. Okay.
Sorry for that. Okay, so where we are. Right. I don't know what was the last you heard. Okay, so yes, as I mentioned, Dan and Jeremy also worked on this model, and what they did, that they gave an alternative derivation of the correlation kernel formula, and also they showed that in some regime the h-scaling limit of the cylindric of the periodic Schur process is given by the finite temperature Airy kernel. Okay, so in both these setups, Q to the volume and shift mix Q to the volume, the height function can be defined as the number of lozenges of non-horizontal type if we go far away down. Then note that in both setups, the height function vanishes if we go far away down, because the boundary conditions are such that all lozenges far away down are horizontal. So there is no lozenges of different type. And if we go far up, then the height function coincide with y coordinate plus a shift, where note that shift does not depend on the x coordinate, but it depends on the Lozenge configuration. And in the unshifted Q to the volume case, we just fixed S to be 0. Okay, so let me actually skip this. And now when we finally know the definitions of the model and all other ingredients, let me remind you of the results. So first of all, we have a limit shape result that we computed the limit shape in both cases for Q to the volume and shift mix Q to the volume. Yet again, recall that the limit shape already was actually computed in Alexei Borodin's paper, but what I need here from the limit shape is to define the liquid region. Note that recall that the liquid region is the region where the probabilities of all types of lozenges are non-zero. So know that by the symmetry of our model, these two probabilities are always the same, and the probability of horizontal one is given in terms of the derivative of the limit shape. So it is clear that, like from this formula, that the liquid region is given by this set. Okay, so we know the limit shape, we know the liquid region, so we can talk about the results for the fluctuations of the height function. So in the unshifted Q to the volume measure case, we showed that the fluctuations converge to the Gaussian free field in a Kenyon-Okounkov conformal structure. And in the shift mix Q to the volume case, recall that we take a shift distributed as a discrete Gaussian variable. So here is the definition. Note that the parameters C and M here are close to the mean and variance as for the Gaussian variable, but not really. They are related, but they're not exactly the mean and variance. So anyway, in the case of the shift mix Q to the volume measure, the fluctuations converge to the Gaussian free field with a discrete Gaussian shift. And now for the rest of the talk, in the remaining 5 or so minutes, I'm going to talk about another model which has similar sorts of behaviors. So let us think about uniform Lozenge tilings of the hexagon with a hole. So note that topologically this domain is equivalent to the cylinder. And there are two different setups how to choose a random tiling of the domain. The first setup is, okay, pick a tiling of a domain uniformly at random. And the second one is, we can fix a height function on the boundary. So know that in this case, we have actually two parts of the boundary. We can fix the height function there and consider Lozenge tilings, which has the height function on the boundary, which coincide with this fixed one. So in the case of simply connected domains, those two setups are the same because the height function on the boundary for simply connected domains do not depend on the Lozenge configuration, which is not the case for these hexagon with a hole, for example. Note that it is clear that on those two pictures, the height of the hole is different. So here, the height of the hole is 2, and here the height of the hole is 3, right? Because here is the height of this stack of cubes is 3, and here is 2. However, on the outer boundary, the height function is the same in both cases. For example, on this part of the boundary, the height is 0, and let's say on this part of the boundary, the height is 5, and this is true in both cases. And the height function on the outer boundary does not depend on the configurations. However, the height of the inner one would depend on the configuration. So there are two setups. And recall that in cylinder, we also have two setups. First, when we think about all tilings of the cylinder, so where we have a shift, And the second is unshifted cylindric partitions, where we can think that shift is fixed to be 0. So these two setups correspond to the tilings of the hexagon, like just all tilings of the hexagon, and tilings with a fixed height function on the inner boundary as well. And there is a nice result by Alexei Bufetov and Vadim Gorin. They proved that for the uniform measure on tilings of the hexagon with a hole, where the height of the hole is fixed, the fluctuations of the height function converges to the Gaussian free field in Kenyon-Okounkov complex structure. And know that this result corresponds to what we have for the unshifted Q to the volume distributed cylindric partitions, where we have indeed the convergence of the fluctuations of the height function also to the Gaussian free field in the Kenyon-Okounkov complex structure. And now what about the uniform tilings where we don't fix the height of the hole? So there is a conjecture made by Vadim that for a general planar, for a general case where the height function of the hole is not fixed, the limiting fluctuations of the hole are discrete Gaussians. And furthermore, the C parameter is given by a Dirichlet energy in the conformal structure, in the Kenyon-Okounkov conformal structure. So zeta here, recall that this is a conformal structure in which fluctuations should converge to the Gaussian free field. And this conjecture is supposed to be proved for some domains in the paper in preparation. I don't know the details, better to ask the authors of this paper, but it fits well with our result about shift mixed Q to the volume measure. Recall that we have there a discrete Gaussian. In addition, we have a Gaussian free field with a discrete Gaussian shift. And indeed, a good analog, natural analog for the height of the hole is our shift S in the cylindric case. And recall that we choose this shift to be distributed as shown here, which actually can be rewritten as an exponent, and then it is equivalently to say that it is a discrete Gaussian with the C parameter given by logarithm t divided by 2, which is exactly a Dirichlet energy computed in the conformal structure which we have in our setup, and it just coincides with this conjecture. So yes. Let me just say a few words about difficulties in the proof of those results. The unshifted Q to the volume measure converges to the Gaussian free field with 0 boundary conditions, so there is no additional shift. But as I said, in this case, we don't have a nice determinantal structure of the Q to the volume measure. However, in the shift mix Q to the volume measure, we have a very nice determinantal structure, but the problem with that, in addition to the Gaussian free field, we have this discrete Gaussian shift, which is not easy to deal with. So what we, how we prove those results, we were jumping back and forth between shift mix Q to the volume and unshifted Q to the volume cases. Using nice formulas for shift mix Q to the volume measure, we deduced formulas for unshifted case and then proved the convergence to the Gaussian free field. And then from this result, we deduced convergence of the fluctuations to the Gaussian prefield with a discrete Gaussian shift. Okay, I guess I am done, and thank you for your attention.